Welcome to Brain Vision.
Hello everyone, this is a solution to problem 15, chapter 24 of college physics. So first, the question is asking us why we need to raise our radar system to a given height in order to be able to detect objects that are close to the Earth's surface. So here, I'd like to first point out the following thing here with these two sketches, is that just because you have a radar doesn't mean that you can detect anything that's coming towards you. The reason for this is that the Earth on which we live has curvature. So if the Earth, to a good approximation, is a circle or a sphere, then you can see that if I put a radar at some height that I call h1 and to some other object, this blob over here, the distance might be obscured by some part of the Earth, and so I will not be able to detect this object. But what happens if I raise the same radar system to a greater height? If I do that, then I might be able to raise it high enough that the curvature or the Earth, curvature of the Earth is not a problem anymore, and so parts of the Earth are not in the way of me detecting this blob. So if I raise it higher, I'm effectively increasing this distance that is known as the horizon distance. So let's call this part D. This is the horizon distance, and so by raising a tower to a bigger height, you can increase this horizon distance. If you were infinitely far away, if this was Earth, and you were infinitely far away over here, then your horizon distance would be such that you can see both parts of the equator, basically. So you would be able to see everything that's kind of happening on the northern or this hemisphere that's facing you. So this is you over here. But if you're closer, then there's going to be some value for this horizon distance, which is how far you can see things coming. So the second part of the question is asking you to estimate how far or how high you need to raise a tower in order for you to see the maximum range of your radar. So here you're not getting your numbers. So really what you want to do is just think about the situation. So I'm modeling the Earth as a sphere. It has a diameter of capital D, which is just 2 times its radius, which is about 6,000 kilometers. And then I'm raising a tower of height h, and this allows me to see a distance or horizon distance d. Now, there's a theorem called the second tangent theorem, whose special case tells you that this horizon distance that you can see is given by this formula. But since we know that we cannot raise towers that are even close or approximately close to the radius of the Earth, we know that this d is going to be way, way, way bigger than h, which means that this bracket over here is dominated by h. So to get approximation, I can say that the horizon distance squared is equal to just the height of the tower times d, which is 2 times the radius. So this is just h, 2 times h times r, to a good approximation. Okay, so that's one thing that we know. Now, what else do we know? We know that this distance has to be traveled by the electromagnetic wave twice in a radar system, and that's given by it's traveling at the speed of light, and the pulse time period is what determines whether you can detect something at this distance or not. So often this pulse time period is given as a frequency, so I'm just going to use the relation again that 1 over t is equal to f. And so this allows me to write distance d as being equal to c over 2 times f. So then if I plug this relation in here, then what I find is that I get c squared over 4f squared. 4f squared is equal to 2 times h times r. And so for a given frequency, to be able to see the horizon distance with your radar, you need to raise a tower of height I'm just rearranging this for h. So this is c squared over 8 f squared times r. So this is how high a tower you need to raise to be able to see things coming towards you at the horizon with a radar system that has a frequency or pulse time or inverse pulse time period of f. So this is the height that you need.